are Team 1 and the name of our project is Robot Laser Tag. Our team members are Evan Clark, Timothy Sharp, Zayeem Zaman, and I'm Zilmara Montecinos. Our project idea came from finding a way to have fun remotely during COVID-19. The main purpose of our laser tag game was to be able to play in different locations. For our project, we need a 3-wheel rover that would move around a course, trying to avoid getting tagged while avoiding obstacles. We're going to use 2 different types of sensors that will help the rover move autonomously. We're also going to have a robotic arm that will be controlled by a player that will be used to tag the rover with a laser. And with the help of a pixie cam mounted in the robotic arm, our game can receive live feedback of where the laser is pointing. This slide shows our design overview. We have 4 main components: the pixie cam, the robotic arm, our sensors, and the 3-wheel rover. Each of these components is driven by a TI-CS 3200 SF board. Our design also includes a Raspberry Pi that serves as our mosquito broker. All of these 4 components are connected to the Raspberry Pi and they're subscribed to different topics. All of the boards publish statistics messages to the broker. However, only the rover and the robotic arm receive commands that come from the camera and the sensors. With this design, we are able to control every component over the internet. The following list are the constraints we had for this project. We had to use TI-CC3200SF boards as processing units. We must use a 2.5 rover with a self-power sensor system. Had to get a robotic arm with 3+ degrees of freedom along with self-power sensor system. We must use an MQTT server to communicate between boards. We had to use a PID algorithm for rover motor control, as well as a Python-based script to monitor the system status. And finally, the rover must move at least 10 feet between 2 locations. Now I'm going to talk about the rover. The rover relies heavily on the commands received from all the sensors mounted on it. We got 3 IR sensors that provide the rover with directions to avoid obstacles in the course. We also have 3 color sensors that serve as targets for the laser and sends commands to the rover when it gets hit to stop for 5 seconds and then resume movement again. The rover is able to receive each of these instructions within 2 seconds of the messages being published to MQTT. In this slide, I have the Python script I wrote to test the rover's wheel movement. As we can see in the video, the first command received is number 4, which is rotate 1, move in the direction of sensor 1. 2 move in the direction of sensor 2, 3 move in the direction of sensor 3, and then 4 rotate again, and finally 0 is to stop. Now each of these messages, as they're published, takes about a little bit less than 2 seconds to be received by the motors and to perform the action. The rover also has 3 Siren 10 motor drivers. These motor drivers have 4 operating modes. For the purpose of our project, we are using mode 4, which is a packetized serial mode that uses TTL level RS-232 serial data to set speed and direction. This driver has the capacity to set different speeds and commands to move forward and backward. In our case, forward is 0 and backward is 1. The speeds can range from 0 to 127, and all these commands are sent via UART. Another component of the rover is the triple LS7366R quadrature counter or encoder buffer. This component drives each of the motor readings of the rover. The encoder receives the MISO, MOSI, and S clock from the TI board, as well as 3 GPIO pins that are used for motor select. The encoder uses SPI communication to read the current tick values from each motor. The way that each motor knows which one is being called is by sending a low signal on one motor while all others stay high. After sending the handshake commands, we set the signal to high again to complete the SPI communication. While the code for this part was written, it failed to run successfully because of problems in the handshake routine of the SPI communication.
The sensor system uses 3 sharp IR sensors for obstacle detection. Each IR sensor is placed between the wheels of the rover. The microcontroller uses the ADC to collect the sensor data, which is then averaged and converted into a distance measurement in centimeters. This distance tells how far away an object is from an IR sensor. The detection range of each sensor is about 10 centimeters to 80 centimeters. However, the program uses 2 thresholds within this range to determine whether or not there is an obstacle within the proximity of the sensor. If an obstacle is within 30 centimeters of a sensor, that sensor becomes blocked, and the rover will not move in that sensor's direction. While the sensor is blocked, it will remain blocked until the sensor is cleared. For a sensor to be cleared, there has to be no obstacles within 35 centimeters of the sensor. The rover will always try to move in the direction of a sensor that has been cleared, but if all the sensors are blocked, then the rover will rotate until the sensor is clear again. The sensor system also uses TCS34725 digital color sensors to detect whether or not the rover has been tagged. Each color sensor contains a 3x4 array of photodetectors. The photodetectors have filters to measure the red, green, blue, and clear components of the incident light. These values are converted into 16-bit digital values with the chip's ADC. The chip then transmits this data through I2C. The rover uses 3 color sensors, and because each sensor has the same I2C address, a TCA9548A I2C multiplexer is used to avoid address conflicts. The RGB values collected from the sensors are normalized against their corresponding clear values. The normalized data is then averaged and compared against threshold values to determine whether or not the rover has been tagged. If the data meets the threshold requirements, then the rover has been tagged and it will stop for 5 seconds before moving again. The navigation task uses a finite state machine to determine what the current navigation command should be. The data from the IR sensors and the color sensors is used to change the state of the FSM and subsequently make navigation decisions. This FSM updates every time the IR sensor data is averaged, or whenever the rover has been tagged. The FSM can be simplified with the following algorithm. If the rover has been tagged, tell the rover to stop for 5 seconds. Otherwise, the rover should move in the direction of a sensor until that sensor detects an obstacle. In that scenario, the rover should then try to move in the direction of a different sensor. However, if all 3 sensors detect objects, then the rover should rotate until at least one sensor detects a clear path. Every time the navigation FSM is evaluated, a navigation command, which is represented by the current state of the FSM, is published to a topic on the MQTT server, which in turn is received by the rover. With this system, the same command will usually be published multiple times. As such, the rover can still navigate correctly even if it misses several navigation messages. The simplicity of this navigation algorithm, however, makes the rover move predictably, which can lower the difficulty of the game.
We created a GUI to help the user monitor board statistics and interact with the camera and the arm. The GUI is written in Python and uses PyQt5. It uses PAHO to handle MQTT publishing and subscribing, and PyQt graphs for the ARM joystick. The way the GUI functions is it contains a callback function that is called whenever the MQTT message comes in. That callback function then can sort between the different topics that the GUI is subscribed to. The main topics it can receive are the statistics for each board, which get written over in these QT labels, and these QT radio buttons, which get turned green and red depending on if the board is active or not. It also gets camera signals, which include one topic for rectangles, which the camera can recognize targets and will send rectangles to where the targets are, and also new pictures. The new pictures are only received if this picture button is pressed, in which case the GUI will send out a message on a camera topic to request a new image. We also have a calibrate site picture, which requests a picture and then searches for the laser pointer, since we have a parallax error in the alignment between the laser and the camera. When the control arm button is enabled, you can use your mouse and drag the joystick around, which will send X and Y coordinate to the arm to tell the arm where the user would like it to move to. The robot arm we used in our design contained 3 PWM servos, which are powered at 5 volts. The PWM signals have a 20 millisecond period and a duty cycle of between 500 and 2500 microseconds. This corresponds to -90 and 90 degrees. The task diagram starts with the MQTT broker, which receives messages from the GUI and sends the X and Y coordinates that it receives through a queue to the user input thread. This thread converts the directional input to target locations for each servo and stores that. A timer is running at 20 milliseconds to let the control servo thread know through another queue when to update the PWM signal, so we can get an updated PWM duty cycle on each new period. When the servo thread receives the timer update, not only does it update the PWM themselves, it also sends a message through this first queue, which lets the user input thread know that it needs to request a new target location for each servo. The user input thread then sends that data through this queue, which is read by the control servo, which is then saved as the new target locations for the servos for the next update cycle. When the servo thread updates the PWM signals, it calculates a new current PWM servo location based on the previous servo location and the target location to make sure that the arm always moves in a smooth manner. There was one issue with these specific types of servos. They have a torque protection, which means that if the screws that are holding the arm together are too tight, or the load is too strong, the torque protection will kick in and force the servos to return to a 0-degree position regardless of the duty cycle. This kicks in after 5 seconds of not moving and having too large of a torque, but as soon as a new update, a new location is given, and the PWM signals change from what it is currently, the arm will snap back to what it should be at.
So for a project, we were required to use a camera to track targets to help a user guide a laser to hit the targets. We decided to use a Pixie Cam for two main reasons. For one thing, other groups have used them in the past, so we knew they were somewhat reliable based off of that. But two, they were also in stock in the lab, so we didn't have to use any of our budget to pay for it, which is really nice. Two main things that it does are image recognition and image processing. For image recognition, basically does is blob detections. It looks for groups of pixels that are about the same color, and based on that, it can kind of keep track of where objects are in the image. For image processing, what it does is the actual camera on this board is actually a relatively high resolution, 1300 by about 1000 pixels, and that's a lot of data to send to something like a microcontroller. So what the board actually does is it scales down the resolution so that it can send a lower res image a lot faster. We decided to use SPI versus UART or I2C just because SPI is the fastest communications method we had available. Here's an example of transaction over a serial interface. You'd have to do something like this whether you use UART or I2C or SPI. This is a function we actually implemented, and what it does is it grabs RGB data from a particular pixel in the image the camera is seeing. So you'd specify an X and Y value of the pixel you want, and then it return the RGB values. One problem this caused was this is a lot of overhead. Just to grab 3 bytes of data, you have to send, in theory, 19 bytes in total. But in practice, you also run into camera latencies. Because we had SPI running at such a high frequency, 20 megahertz, which is the limit the microcontroller would go to, the camera actually wouldn't be able to respond instantly. So there would be a bunch of bytes after the request where it's just sending zeros, waiting to figure out a response. In practice, it actually turned out to be 50 bytes of data just to grab 3 bytes of data, and this really slowed down image transfer when you're trying to upload an image to the GUI. In practice, what we ended up doing is we scaled the resolution additionally ourselves. We only sent about a fourth of pixels, so the resolution was scaled by a fourth, which made it 4 times faster. One other problem we ran into, which we were completely not expecting, was transmission line effects. We were using a logic analyzer to check if the signals being sent on the wires for SPI were correct values. But it turned out that the measurement device itself was actually interfering with the signals and messing up the data. So once we disconnected that, it started performing properly. In order to let all of our devices communicate with each other, we use a message protocol called MQTT. MQTT is designed for IoT devices. It's designed to be lightweight and reliable. And it uses a publish and subscribe model. So the way it works is any device connected to the broker can publish a message to a specific topic, and any device that subscribes to that topic can receive that message. So potentially one device could publish a message and all devices could receive that message at the same time. So we use software called Mosquito to run a broker on a Raspberry Pi. Now normally during pre-COVID times, we would have that broker connected to a local Wi-Fi router, and we would have all of our microcontrollers connected to that router, and we would all communicate with each other that way. However, because of COVID and because we were all working remotely, we were all connected to different Wi-Fi routers, and this caused a big problem. Specifically, network address translation. Because we were all connected to different routers, we were all connected to different subnetworks. So we had different sets of IP addresses, and we couldn't directly communicate with each other. There are 2 solutions for this. One is to use a public broker hosted by a public server. There are a number of free MQTT brokers available online that you could access. However, a couple of problems with these. One problem was reliability. We found when we were trying out that several times the server would crash and we would have to reconfigure all of our components to access a new server. So that was really annoying. Another thing is it's not safe. Because it's public, literally anyone could connect to it, subscribe and see what topics are there, and just publish anything they want. So anyone on the internet could just come and mess with our stuff if they want to, and we really want to avoid that if possible. So we ended up going with the second possible solution we found, which was use tunneling. We use a software called ngrok, and the way it works is it has software running locally on the Raspberry Pi, and then it has a service which will generate a unique URL and port number. The way it works is we all send MQTT traffic to that particular URL and port, and it forwards it through the Wi-Fi router to the broker. That way, it let us have our own private brokers, which we could configure it however we wanted, And it was more reliable because if it went down, then we could just fix it ourselves. And it was safer because for one thing, we could monitor it, and for another thing, we configured it to require a username and password for MQTT. So people had to have the right username and password in order to be able to publish or subscribe any messages.